So this is 13.2 part B. The last colligative property we're going to look at right now is osmotic pressure, and then we're also going to throw in, well, how do electrolytes change our colligative properties? So first off, a few definitions. Semipermeable membrane, it does allow the passage of some particles while blocking the passage of others, so it's going to depend on the size of your particle, what can get through the membrane. And the movement of solvent through a semipermeable membrane from the side of lower solute concentration to higher solute concentration is called osmosis. So again, the key to osmosis is going to be low solute concentration to high solute concentration. Low to high is going to be the direction of our movement. And osmotic pressure is the external pressure that must be applied to stop osmosis. So how much pressure is applied to stop osmosis? Let's see here. Doesn't look like this animation works, but in this one right here, it's going to show that your membrane does allow certain molecule types like water to get through it, but larger molecules would not be able to get through the semipermeable membrane, so no larger molecules or ions. And then again, this one right here, the osmotic balance that we would look at here, osmotic balance, water, which is our solvent, passes from low solute concentration to high solute concentration. So you would see your water go from low to high solute concentration. And you can see in this a couple of water molecules that are already starting to move through the membrane. So we had mentioned Rao's law earlier in section 1, so we're going to bring it up again here. As I look at these two, if I look there on the left, you have a semipermeable membrane in place right along here. You have pure water on the right side, and then you have a sugar solution there on the left side. And it says when pure water, I'm just reading right down here, when pure water and the sugar solution are separated, the net movement of water through the membrane is from the pure water side into the aqueous solution. So we're going from low concentration to high concentration, and you're going to see that the movement of water is in that direction, and you can see the majority of your arrows are moving in that direction. And it says the level of solution rises. The level of solution rises until pressure exerted by the height of the solution. Again, the word solution indicates solute plus solvent. So this side is our solution. The level of the solution rises until the pressure exerted by the height of the solution equals the osmotic pressure, at which point no net movement of water molecules occurs. So when it says no net movement, you're still going to have water molecules that move back and forth through the membrane, but it's going to equalize itself as far as that movement. So again, the solution rises until, and when we talk about the solution rising, notice the height of this solution is now higher than what it was right over there on the left. The solution rises until the pressure exerted by the height of the solution equals osmotic pressure. So I would definitely make sure that you get this written down so that you know what's going on there. So that is osmotic pressure in a nutshell. Again, also goes back and correlates to Rao's law. Let's move on to our electrolytes. So electrolytes will depress freezing point and elevate boiling point of a solvent more than expected. In our previous calculations earlier in this section, for part A of it, we looked at non-electrolyte solutions. So non-electrolytes do not conduct electricity, whereas electrolyte solutions will conduct electricity, and it's because electrolytes will produce more than 1 mole of a solute. They will break into ions if it will produce electrolytes so that electricity can be conducted. So we're going to look at a few examples, and one of them is backwards, so I will make that correction right now. But as I'm looking at these, sugar dissolved in water is still sugar, so that is considered to be a non-electrolyte. So there's only one molecule. In this next one, calcium chloride, which is an ionic compound, breaks into the calcium ion and 2 chloride ions, so 1 plus 2 is 3. So the number of moles of solute is actually 3. And then in that other one there below, that is NaCl, which is also an ionic compound, breaks into 1 ion of sodium, 1 ion of chlorine. 1 plus 1 is 2, because I'm looking at any coefficients that would be right out here in front. Okay, any coefficients in front. So that one is actually 2, so there was a typo here on this particular one. So again, ionic compounds will break down into ions, making themselves electrolytes. And we will even talk about more electrolytes in the next chapter or two that we get to. So ionic compounds, they will depress our freezing point more than expected. They will elevate the boiling point more than expected. We'll get to an example here in a moment. So your colligative properties do depend on the total concentration of solute particles, and the changes to these properties caused by the electrolytes will be proportional to the total molality of all dissolved particles. So it is proportional to the total molality. And for the same molal concentration of sucrose and sodium chloride, again, sucrose is a covalently bonded set of atoms, so sugar, all nonmetals bonded together, versus sodium chloride, that's a metal and a nonmetal, it's an ionic compound. You would expect the effect of the colligative properties to be twice as large for sodium chloride as for sucrose, again, because one's an electrolyte and the other's a non-electrolyte. So if we look at our example, make sure you get this example written down in your notes and any work that we do with it. You are going to need your molal, freezing point, boiling point constants table that you should have a copy of by now. What's the expected change in the freezing point of water in a solution of 62.5 grams of barium nitrate in 1 kilogram of water? So again, solute in solvent. If I'm looking at all of this right here, expected change in freezing point, a change, that's your delta. So delta TF is what we need to calculate here. And to do that, we have KF times, so that's our constant, times the molality. We are adding an additional segment to this called N, where N is equal to the number of ions in solution. Number of ions in solution. So we have added an extra piece to this. So if you want to label this compared to what we had earlier, you could also label it as number of particles that will end up being in solution. So for this particular one, we had said that your KF is based on the solvent. Your M, well, that's a mixture of the two. Molality is moles of solute over kilograms of solvent. Your N is strictly based on your solute only. So KF for solvent, N is solute. If I'm looking at this, my solute is barium nitrate. That is an ionic compound. We have a metal and a polyatomic ion. So when it breaks down, we will have 1 barium ion and we will have 2 nitrate ions. So 1 plus 2 is 3. So N will be equal to 3 in this particular example. So we were looking at, we needed to find delta TF, molal freezing point constant times the molality times N, which is our number of particles of solute. To do that, we have to calculate M first. So molality, that is moles of solute over kilograms of solvent. And as I look at that, we can easily get kilograms of solvent because it tells us we have 1 kilogram of water. Water is our solvent. The solute, though, is barium nitrate, and it says we have 62.5 grams of barium nitrate. So we've got to convert grams to moles. So I'm going to head over and do that first and convert grams to moles so that we have that particular value. So 62.5 grams of barium nitrate. Again, I'm not going to write out barium nitrate. You can do that in your notes, but we do need to get grams to moles. And the molar mass of barium nitrate is, this is from the periodic table. I've added up all the masses for barium nitrate, 261.35 grams. Make sure you can get that. So our molar mass is 0.239 moles. So I'm going to go over and plug that in, 0.239 moles of solute over kilograms of solvent, which we had 1 kilogram of water. So the molality ends up being still 0.239 since we are dividing by 1. Okay, let's go plug that in. So molality, 0.239. If I look at my freezing point constant of water, we know that the freezing point constant of water is negative 1.86. And again, that's coming from the chart, and it's got to be for our solvent, water. And then our value of N, as we discussed earlier, barium nitrate breaks down into 3 different ions. So the number of particles is 3. So the freezing point depression, or delta TF, ends up being negative 1.33 degrees Celsius. So if it asked for the new freezing point, we're going to do that even though it does not ask for that. But again, I want you to see it one more time. So the new freezing point of water, once we added that solute to it, I look back at my chart. The normal freezing point of water is 0.00 degrees Celsius. We add on the delta TF. So the new freezing point, negative 1.33 degrees Celsius. Please make sure you get all of this in your notes. So again, this right here is just giving you some ideas of, we've got 3 different solutes. If I were to break it down for this one, because there is something that I do want you to notice as we look at this. KCl, its N value is 2. Magnesium sulfate, its N value is also 2 because the sulfate ion stays intact as SO4, but there's 1 of each, magnesium and sulfate. And then N equals 3 for the barium chloride. They're taking 3 equal sets of concentrations here, and it gives you the observed delta TF. Notice that the delta TF between KCl and MgSO4 is not the same. And it's telling you also below here the actual values of colligative properties for all strong electrolytes are almost what would be expected based on the number of particles they produce in solution. But we will talk about this on the next part. Again, if it's N equal 2 versus N equals 3, if I were to split those just like that, you can see that the delta TF is definitely more than what you see for for the N equals 3 versus N equals 2. But what accounts for that difference in our KCl and MgSO4, even though both of those are N equals 2? Why the change in temperature that is going to be a little bit different between those two? So we're going to talk about it on the next slide. So the difference between the expected and calculated values are caused by the attractive forces that exist between dissociated ions in aqueous solutions. So we're looking at attractive forces between the ions. According to, I don't really know how to say their names, we'll say Debye and Huckel, a cluster of hydrated ions can act as a single unit rather than as individual ions. That causes the effective total concentration to be less than expected. So in the previous example, when we looked at it, this cluster of hydrated ions, that's that SO4 cluster we were looking at. So even though its value of N is 2, it acted more like the KCl. So the cluster of hydrated ions can act as a single unit rather than individual, so we leave sulfate intact, causing our effective total concentration to be less than expected. And then this last bullet point, ions of higher charge have lower effective concentrations than ions with a smaller charge. So if we were to look at BaCl2, which was higher than KCl, but it wasn't 1.5 times higher. So if I look at that, BaCl2, the value was 3, KCl, our N value was 2, but when you look back at the concentrations, BaCl2 wasn't 1.5 times higher than what KCl was. That's because, based on this particular one right here, barium has a 2+ charge. Because of its higher charge, where K is only a plus charge, and notice they both share the chloride ion, ions of a higher charge will have lower effective concentrations than ions with a similar charge. So the barium with its 2+ charge, again, even though you have more ions, it doesn't go 1.5 times higher or 3/2 higher.